Today we'll be working on significant digits and scientific notation, lesson 32. Here's your little warm-up. You can feel free to send me your answers. So there is going to be a lot of note-taking for this, so you can pause it and then press play once you're ready to go through it. But measurements are always approximate, never exact. We don't have a great way to be exactly exact with our technology when it comes to rulers and tape measures and gallons and those kind of things. So precision describes just how close we are to the reality of what you're trying to measure. And significant digits, I'll also say sig figs or significant figures often, because that's how I learned it, will tell us how precise we need to be. So there's different numbers that we use in measuring. For example, if my pencil is 4 inches long, that is an approximate measure of 4 inches. Like the 4 represents 4 inches. But if we talk about 4 pencils lined up, that 4 is no longer a measurement. That is what we would call like a whole number or a counting number. So it tells us there are 4 pencils in total, but it doesn't tell us how long something is, how big something is. That there's no units tied to that number. And that's an important distinction going forward, especially with significant digits. So when we're looking at significant digits, all digits except 0 are significant, but there's even a caveat to that, which we'll get to. So that first example, 13 and 125 thousandths, has 5 significant digits. So those 5 numbers are what we're going to call significant digits, which then helps us in the future of how to make sure we're being precise with our measurement. But sometimes zeros are significant. If the 0 is between 2 numbers, it's an SD. If the 0 is a placeholder, which means between the decimal point and the number, it is not an SD. So a couple examples here. For that first one, that would be like 105. That would be 3 significant digits. For the second one, 150 would be 2 significant digits, because that 0 is just a placeholder. It's not actual in the number. Then if the 0 is to the right of a decimal point, so 15.0, then that 0 is a significant digit because it's expressing precision. It's telling us that our answer was to a tenth already, so we need to keep it to the tenths. For all of these, when we're adding, subtracting, multiplying, and dividing, the answer can only be as accurate as the least precise component. So for that first one, we see that 4 1/10 plus 2 333 thousandths would round down to 6 4/10. Even though this measurement here is much more precise, that's going down to the thousandths, so it's a very small detail. We can only put our answer to the most basic significant digits. Same thing with multiplying. Here this has 2, this one has 4, but as you see our answer would then have 2 significant digits, so we would round this to 96. Next one, there's 3 there, so that would be 4 and 11 hundredths. And remember, if one of the numbers is a whole number, so thinking back to that 4 pencils, where 4 doesn't actually have a measurement to it, it's just representing how many things we have, that does not count towards significant digits. So that's like, if you were going to do, you wanted to measure 2 2/10 inches 4 times, well, that would be 8.8 inches, and that would be your significant digits, because this doesn't count for significant digits. Then we have scientific notation, just helps us be able to do problems with very large or very small numbers without having to write out every single part. So exponential notation, working into scientific notation, don't worry, we're still on scientific notation, it helps us separate the digit from the place value. So we would write 93 million as 9 times 10 to the 7th, which means there's 3, 6, 7 place values after the 9, plus 6 times 10 to the 6, which means there's 3, 6 place values after the 3. That is exponential notation, which then can help us understand scientific notation. So for scientific notation, we're going to keep looking at that 93 million. We're going to keep the 9 and 3 together. We'll place a decimal between them so that 9 becomes the unit spot. So we'll do 9 3/10. We call these the mantissa. That's the significant digits, and that tells us how many spots to round to. And then we'll write the rest of this that comes after the decimal point as multiplying by 10 times 7, because there was 1, 2, 3, 4, 5, 6, 7 place values to put that decimal between the 9 and the 3. The exponent is referred to as the characteristic. So here are some examples of scientific notation. You might want to pause the video so that you can take a minute to look at them all and see what things you notice. So when we compute, when we actually do math with scientific notation, what's nice about this is all multiplication here. So we could, I'm going to be writing a lot of steps for this problem. You don't normally need to write this many. So that's times 2 times 10 squared. That is the same problem. We're not distributing here because there's no plus or minus inside. When it's multiplication, it's just straight multiplication all the way across. Then we can rearrange this. 9 3/10 times 2 times 10 to the 7th times 10 squared. This one becomes 18 6/10. That's what these multiply to. These ones become 10 to the 9th, not to the 7th. 10 to the 9th. And then remember, because of how significant digits work, we gotta look at the smallest one. But what we didn't talk about here is the context of this is how far away we are from the sun. This is represented if we want to do 200 and times that distance. So really this is what we would consider a whole number, a counting number. So the sig figs here, or the significant digits, is 9.3, which is 2. So this would become 19 times 10 to the 9th, but then we need to put a decimal in between that 1 and the 9. So we got 1.9 times 10 to the 10th. Because we moved the decimal over once, we have to add 1 to the 9. All right, so we're just going to practice writing these in scientific notation. So this would be a movement of 1, 2, 3, 4. Since we moved to the right, that's 10 to the negative 4. Here we're going to change both of these to scientific notation first. So this is 3, 6, 7 times 1, 2, 3, 4, 5, 2.3 times 10 to the 5th. Now you multiply like things together, so we can multiply these, which would be 6 and 9/10, and then multiply these together. Oh wait, but that's negative 5, because that was to the right. So that would be times 10 squared. Then we want to check our significant digits here. I keep on saying sig figs, which is 1. This has a sig fig of 1. This has a sig fig or significant digits of 2. Remember, we don't count the zeros. Actually, this one would be 3, 6. Sorry, we do count the zeros there. This is 6, this is 2. So we take the smaller. So 6.9 would be our answer. Or sorry, 7.0. That's not 2. I missed that. That's 1. Which would be 7 times 10 squared. We've already done this one. 9.3 times 10 to the 7th. Times 5.47 times 10 to the 1, 2, 3, 4. Negative 4. There's 2 significant digits here because of this 93. So we're going to be keeping it 2 here. So we'll do 9.3 times 5.47 times 10 to the 7th times 10 to the negative 4th. Multiply those together. So we got 50.871 times 10 to the third. And we said 2 sig figs, so that would be 5.1 times 10 to the third. Or to the fourth on that one, because we have to move this once to the left, so we add 1 up here. Last one, division. 2.8. That's 3, 6, 7, 8. Divided by 1, 2, 3, 4. So we're going to divide like things here. So we'll have 2.8 divided by 7 times 10 to the 8th divided by 10 to the negative 4th. That first one's going to be 0.4, and the second one is going to be 10 to the 12th. And then there are 2 significant digits here, so we want to move this to the right 2 times. So it'll be 4.0 times 10 to the 10th.